Hey guys, welcome. This is our 12.1 video, and we're going to start with a little vocab. So we want to actually get this piece right here down. We are talking about tangent. Tangent is not related to our ratios like sine, cosine, tangent when we're talking about our circles, but tangent is has something to do with our circles. So draw this picture and draw these two definitions, but a tangent to a circle is a line in the plane that intersects in exactly one location. So point B, it only hits it one time. So a diameter would go through a circle and hit it twice. This is a line that's outside of the circle and hits it only once. And then the point of tangency is where the circle and that line meet. Okay. So we're going to go ahead and talk about a couple theorems that are related to our tangent. Okay, so our first one, and I'm actually going to make this a little bit bigger, put my head over here. So we have our first theorem here, and it says if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So if we have a tangent line, the radius and the tangent line are going to form a 90 degree. Okay? Always, every single time. So we can actually use this information a lot to help us. We know a lot about stuff with 90 degrees, so this is very useful to us. Next, in a line, if a line in the plane of a circle is perpendicular to a radius at its endpoint in a circle, then the line is tangent to the circle. So we could actually say this is a converse theorem of our last one. So if tangent, then radius is perpendicular. If radius is perpendicular to a line, then tangent. So we can do kind of the inverse, or sorry, the converse of those two. All right, and then we get another one here, and it kind of squeezes off a little bit on the page. I might actually minimize this and its size. So if two tangent segments in a circle share a common endpoint, so we have B, outside of the circle, then the two segments are congruent. So BA and BC would be congruent segments. So we're going to take a look at a couple examples where we are going to utilize these pieces of information within our tangent part, and let's see if we can get to it. So first one, finding angle measure. So let's take a look at this picture here. ML and MN are tangent. Okay, so a couple things we know. We do know that these two segments are going to be congruent based upon one of our theorems. But what is the value of x? Okay, well, if you see, we actually create ONML is a quadrilateral. And we know quadrilaterals, the sum of quadrilaterals, so the sum of, we'll just say, a quadrilateral. Why not? The sum of a quadrilateral is 360 degrees. And so we also know that a radius and a tangent are always going to meet at a 90. So these are 90 degrees right in here and right in there. And so we can actually add up all these and set them equal to 360. So we get 90 plus 90 plus 117. That's a horrible looking 7. Plus x equals 360, and then we can just go ahead and add them up and subtract from 180. Or sorry, 360, not 180. And we get the value of x to be 63 degrees. Okay. So again, we use that whole concept of that the radius is perpendicular to the tangent to get that extra 90 degree. All right, let's look at our next one. Okay, so next problem is what is the distance to the horizon that a person can see on a clear day from an airplane 2 miles above Earth? Earth's radius is about 4,000 miles. So this is a little tricky. We want to go ahead and first draw a circle. Okay, and then we're going to draw the center of the circle. And what we're going to do is we're actually going to shoot straight up here, and that's the radius, and that's 4,000 miles is the radius of our Earth. And then we're going to go an additional 2 miles up to our airplane. Okay, so there's our airplane in the sky, and that's 2 miles there. And we're saying, what is the distance to the horizon that a person can see? So that distance is actually going to be a tangent line, right? So that's going to hit right there at one part. And so we want to know what this distance is here, and we know from here to here, and this would be perpendicular. Okay, again, tangents create perpendicular segments right there, and we want to find out what that is. Well, the radius here is also going to be 4,000, and so what we need to do is use our Pythagorean theorem. We have a right triangle. So we are going to go ahead and just do x squared plus 4,000 squared equals 4,002 squared. So that would be our hypotenuse across from it. So 4,000 squared minus 4,002 squared minus 4,000 squared. Okay, so we could go ahead and calculate that. 4,002 squared minus 4,000 squared right there. I'm going to get us 16,004 equals x squared. And then we're just going to go ahead and take the square root of it. And it doesn't say at how many degrees we want, but we can just take the square root of this answer. And we're going to get x is going to be about 126.5 miles. So if you're 2 miles up in the air and you look straight out in front of you to the horizon, the distance would be 126.5 miles, which is kind of cool. Let's take a look at our next one. Okay, so this is our last one here, and we have a circle O, which you see is inscribed inside triangle ABC. What is the perimeter of the triangle? So inscribed means each of those lines are only hitting them at one point. And so what we know is that, according to our theorem, is that if we have a mutual point on the outside and they're tangent to both, they're equidistant. So we can go ahead, and if that's 10, we know this is 10. If that's 8, we know this is 8. And if that's 15, then this is 15. So it's just kind of a little shortcut. So we get to basically do 10, and there's 2 of those, plus 2 of the 8s, and plus 2 of the 15s. And once we add all those up, that's going to be 20, 16, 30, I believe we end up with 66 centimeters for our perimeter, which is the distance around the triangle. Alright, so that's pretty much it. We'll get into some more problems in class, and have a good one. And that's how the cookie crumbles.